Right now, more than 25 billion kilometers from Earth, a spacecraft built in the 1970s is broadcasting a radio signal using a transmitter about as powerful as a refrigerator light bulb. By the time that signal crosses the unimaginable distance between Voyager 1 and Earth, its strength has dropped to less than 1 attowatt, a billionth of a watt. To put that number in terms an engineer might actually use, the power NASA's antennas receive from Voyager 1 is roughly 20 billion times weaker than what it takes just to run a digital watch. By any ordinary standard of radio engineering, a signal that faint shouldn't be recoverable at all. It should simply vanish into the background noise of the universe, the natural static generated by everything from distant galaxies to the Earth's own atmosphere to the thermal jitter inside a receiver's own electronics. And yet, more than 4 decades after launch, NASA's Deep Space Network still picks it up, tracks it, and in most cases, still decodes real, usable information out of it. This isn't an exaggeration dressed up for a thumbnail. The numbers involved are genuinely, technically extreme, verified by NASA's own scientists, and independently confirmed by outside researchers using entirely different equipment. This is the story of exactly how faint Voyager 1's signal really is, the extraordinary engineering required to hear it at all, and why, even with all of that ingenuity, the day is coming when even the best receivers on Earth won't be able to hear it anymore. Every part of the story is documented, verifiable, and confirmed by multiple independent sources, including, remarkably, a team of hobbyists working with equipment built decades before Voyager 1 even existed. To understand why this signal is so extraordinarily faint, you first need to understand exactly what's generating it, and just how little power Voyager 1 actually has left to work with. Voyager 1 launched on September 5th, 1977, and communicates with Earth using a radio transmitter with an output of about 4 watts, roughly comparable to the power draw of a small household light bulb, or, as some engineers have described it, not far off from the bulb inside a refrigerator. That's the entire broadcasting power behind every photo, every scientific measurement, and every status update the spacecraft has ever sent back across more than 4.5 decades of operation. There was never a realistic option to make that transmitter significantly more powerful. Every extra watt of broadcast power requires additional equipment, additional mass, and additional electricity that Voyager's onboard power supply, a radioisotope thermoelectric generator converting the heat of decaying plutonium into electricity, simply couldn't spare, especially since that same power source has been steadily, irreversibly weakening for nearly 50 straight years. That power source is central to the whole story. Voyager 1's generator loses a small amount of output every year, with absolutely no way to refuel or recharge it, ever. To conserve what little electricity remains, NASA has had to permanently shut down instrument after instrument over the decades, including, as recently as April of 2026, the Low-Energy Charged Particles Instrument, which had been operating almost continuously since 1977. Every one of those sacrifices exists specifically to keep the spacecraft's heaters running and its transmitter broadcasting for as long as physically possible. In other words, the faintness of Voyager 1's signal isn't a flaw or an oversight. It's the direct, unavoidable consequence of squeezing nearly 50 years of operation out of a power source that was never designed to last remotely this long. It's worth appreciating just how deliberately conservative Voyager's original engineers had to be, decades before anyone could have known the spacecraft would still be operating this far into the 21st century. Every design choice on Voyager 1 reflects a fundamental trade-off between capability and long-term survivability. A more powerful transmitter would have meant faster, more reliable communication in the spacecraft's early years, but at the cost of burning through its limited, irreplaceable power supply that much faster. Instead, engineers chose a modest transmitter output paired with an efficient, tightly focused antenna design, betting on precision rather than brute force, a bet that nearly 50 years later has paid off in a way nobody at the time could have fully anticipated. On the receiving end, Voyager 1 also carries a 3i, 7-meter high-gain antenna, a parabolic dish specifically designed to focus its limited transmitter power into as narrow and precisely aimed a beam as possible, rather than broadcasting weakly in every direction at once. That focused beam is what makes any of this even theoretically possible, but focusing the beam only helps so much when the beam itself still has to travel across more than 25 billion kilometers of empty space before anything on Earth ever has a chance to catch it. Let's walk through exactly how weak Voyager 1's signal becomes by the time it reaches Earth, because the actual numbers involved are almost difficult to hold in your head. Radio signals weaken with the square of distance, meaning if you double the distance a signal travels, its strength doesn't just halve, it drops to a quarter of what it was. Over a distance of more than 25 billion kilometers, that effect compounds into something almost absurd. According to reporting based on interviews with engineers at NASA's Jet Propulsion Laboratory, Voyager 1's 22. 4-watt signal, by the time it crosses that entire distance and reaches Earth, has been reduced to roughly 1/10 of a billionth of a watt. a unit of power so small it's typically measured in attawatts, where a single attawatt is 1/100000th of 1/10000000th of a full watt. The National Radio Astronomy Observatory has independently confirmed figures in this same range, describing Voyager 1's received signal strength as similarly measured in fractions of an attawatt. To put that number in terms that might actually mean something in daily life, NASA's own public education materials state plainly that the power the Deep Space Network's antennas receive from Voyager's signals is roughly 20 billion times weaker than the power required just to run a simple digital watch. Separately, tracking data from 2017 placed Voyager 1's received signal strength at approximately negative 160, 48 dBm, a decibel-based unit engineers use to measure extremely small amounts of power, which works out to being roughly 1,000 times weaker than the signal your car radio picks up from a typical local FM station. And every single year, as Voyager 1 continues drifting further away, that number keeps getting weaker still, purely because of the relentless mathematical reality of distance. It's worth pausing to appreciate just how much engineering stands between a signal this faint exists and NASA can actually do anything useful with it. Simply detecting that a signal is present at all, admittedly, is already remarkable. But NASA doesn't just detect Voyager 1's carrier signal. In most operating conditions, engineers can still extract genuine, structured data from it. Telemetry describing the spacecraft's health, and scientific readings from its 2 remaining active instruments. Recovering actual information from a signal this faint, rather than just confirming a signal exists, represents an entirely different, considerably more difficult level of engineering achievement. To offer one more useful comparison for scale, a typical smartphone sitting in your pocket transmits at a power somewhere in the range of a fraction of a watt up to around 1 or 2 watts, depending on signal conditions, and it still needs to be within a few kilometers of a cell tower to maintain a reliable connection. Voyager 1, using a transmitter roughly 10 to 20 times more powerful than a phone, still has to cross a distance more than 5 trillion times greater than the distance between a phone and its nearest tower. That's the scale of the challenge Deep Space Network engineers are actually solving every single day, almost without public fanfare, simply as a routine part of keeping Voyager 1's mission alive. Here's where the story shifts from "this sounds impossible" to "here's exactly how it's actually done." And the answer involves some of the most sophisticated radio engineering humanity has ever built. NASA's primary tool for this task is the Deep Space Network, officially described by NASA as the agency's international array of antennas for communicating with missions beyond Earth's orbit. Rather than relying on a single antenna anywhere on the planet, the network operates 3 separate complexes, positioned in Goldstone, California, Madrid, Spain, and Canberra, Australia, spaced roughly 120 degrees apart in longitude. That specific spacing isn't arbitrary. As Earth rotates on its axis, a distant spacecraft like Voyager 1 will eventually set below the horizon at one complex. But by the time it does, it has already risen into view of the next complex further around the globe. In effect, the rotation of the entire planet becomes part of the communication system itself, creating a continuous relay that ensures Voyager 1 is essentially always within view of at least one listening station on Earth. Each of these 3 complexes includes a massive 70-meter dish antenna, among the largest steerable parabolic antennas ever constructed, specifically built to maximize the sheer physical area available for collecting extraordinarily faint radio signals. According to NASA's own materials, the 70-meter dish at the Canberra complex in Australia, designated DSS-43, holds particular importance for the Voyager missions, since it's specifically equipped with the transmitter power and frequency capability needed to send new commands to Voyager 2 out in interstellar space, a role no other antenna on the network is currently able to fill in quite the same way. Alongside each massive 70-meter dish, every complex also operates multiple smaller 34-meter antennas, which can be electronically combined, or arrayed, with the larger dish to further boost overall sensitivity when an especially faint or important signal needs every possible advantage. That arraying technique deserves a bit more explanation, because it's a genuinely clever piece of engineering in its own right. Rather than relying on a single antenna's collecting area alone, engineers can combine the signal captured by several separate dishes simultaneously, precisely timing and aligning each antenna's received signal so they reinforce each other rather than canceling out, effectively creating a single, much larger virtual antenna out of several physically separate ones. The same fundamental technique, known more broadly as interferometry, is also what allows radio astronomers elsewhere in the field to achieve resolving power far beyond what any single dish could manage on its own. For a mission as demanding as tracking Voyager 1's ever-weakening signal, every antenna the network can bring to bear, arrayed together, meaningfully improves the odds of successfully recovering usable data during especially difficult tracking passes. There's also a scheduling challenge layered on top of all this technical complexity that rarely gets much attention. The Deep Space Network doesn't exist solely to serve Voyager 1. Dozens of active NASA missions, along with partner missions from other space agencies, all compete for a finite number of antenna hours across the network's 3 complexes every single day. Allocating enough dedicated tracking time to reliably capture Voyager 1's signal, especially during any period of unusual difficulty or troubleshooting, requires careful, ongoing coordination among mission planners, balancing Voyager's needs against the needs of dozens of other spacecraft, simultaneously relying on the exact same limited global infrastructure. But size alone isn't enough. A large dish increases how much of a faint signal's energy can physically be collected. But actually extracting useful information out of a signal this week requires solving an entirely separate problem: separating that whisper-quiet signal from every other source of radio noise in the environment, including noise generated by the receiving equipment itself. To manage that, the Deep Space Network relies on extraordinarily sensitive receivers, often cryogenically cooled to extremely low temperatures, specifically to minimize the random thermal noise that any electronic system naturally generates simply by existing at normal temperatures. Behind those receivers, precision digital signal processing systems work to identify, isolate, and decode Voyager 1's specific narrowband tone, while accounting for the subtle Doppler shift in frequency caused by the constant relative motion between Earth and the spacecraft as both move through space. None of this happens automatically or effortlessly. It represents the accumulated result of decades of refinement in one of the most specialized fields of engineering on the planet. It's not just NASA's own professional equipment that can pull off something like this either. In a genuinely remarkable demonstration of just how achievable this kind of detection has become with the right technique, a team of amateur radio astronomers in the Netherlands, working through an organization called 1’s, successfully tracked Voyager 1's faint signal using the Dwingaloo telescope, a radio telescope originally built back in 1956, decades before Voyager 1 even launched. By carefully calculating precise orbital predictions for where Voyager 1 should be and adapting their vintage equipment with a newly mounted antenna specifically tuned to Voyager 1's transmission frequency, this non-professional team successfully picked up the spacecraft's carrier signal across a distance of roughly 9 billion kilometers, proof that, with sufficiently careful technique, this achievement isn't limited exclusively to NASA's own most advanced government facilities. That capability was put to a genuine, real-world test in 2024. In October of that year, NASA temporarily lost contact with Voyager 1 after an issue with the spacecraft's onboard fault protection system caused it to switch over to a weaker backup transmitter operating on a different radio frequency, known as the S-band, instead of its primary, stronger X-band system. Because the S-band signal is considerably fainter and more difficult to detect than Voyager 1's usual transmission, re-establishing contact required the Deep Space Network team to carefully locate the spacecraft using that weaker signal first, before successfully commanding it to switch back to its stronger, more reliable transmitter. Contact was fully restored by October 24, 2024, a genuine demonstration of exactly how much margin, skill, and redundancy is built into this entire communication system, since even a signal fainter than Voyager's already extraordinarily weak normal transmission still proved detectable and recoverable. That specific incident is worth dwelling on a little longer, because it illustrates something important about the layered redundancy engineers built into Voyager's design decades before any of this happened. The fault protection system that triggered the switch to the weaker S-band transmitter exists specifically as an automated safeguard, designed to protect the spacecraft from a range of possible malfunctions by falling back to a simpler, lower-power operating mode whenever certain unexpected conditions are detected. That system worked exactly as intended in 2024. It correctly identified a problem and responded by protecting the spacecraft, even though it wasn't clear to engineers on the ground exactly what had triggered it in the first place. The challenge that followed wasn't a spacecraft failure in the traditional sense. It was a communications puzzle, requiring the Deep Space Network team to essentially relocate an extremely faint, unexpected signal somewhere in the sky using the same techniques described earlier before they could even begin working through what had actually happened on board. That the team pulled off exactly that, working with a signal weaker than what NASA already considers its normal, extraordinarily difficult baseline, speaks to just how much operational depth and experience the Deep Space Network team has built up over Voyager's remarkably long operational history. It's worth stepping back and asking why this specific engineering challenge deserves this much appreciation, beyond simply being an impressive numbers game. Because every technique refined to keep hearing Voyager 1's fading signal directly benefits every other deep space mission NASA operates or plans to operate in the future. The same Deep Space Network infrastructure, the globally distributed antenna complexes, the cryogenically cooled receivers, the precision signal processing techniques originally pushed to their limits by the unique challenge of tracking Voyager, is the exact same infrastructure relied upon by missions studying Mars, Jupiter, Saturn, and every spacecraft venturing beyond Earth's immediate vicinity. Voyager 1, simply by being so far away and so faint for so long, has effectively served as an ongoing real-world stress test for deep space communication technology for nearly 5 decades, continuously pushing engineers to improve sensitivity and precision well beyond what any closer, stronger signaled mission would ever have demanded on its own. There's also a genuinely significant operational challenge layered on top of the raw signal detection problem, the sheer time delay involved. At Voyager 1's current distance, a radio signal traveling at the speed of light takes approximately 23 hours to complete a one-way trip, meaning any command sent to the spacecraft and any response sent back in reply together make up a round-trip communication cycle stretching to nearly 2 full days. Engineers cannot make real-time adjustments or corrections the way they might with a nearer spacecraft. Every command has to be prepared with total confidence in advance, transmitted into the silence, and then followed by an agonizing wait of almost 48 hours before any confirmation of success or failure comes back. That delay reshapes the entire culture of how the mission team operates, in ways that are easy to overlook from the outside. Every proposed command sequence goes through extensive review and simulation before it's ever actually transmitted, precisely because there's no opportunity to catch and correct a mistake in the moment the way engineers working with a nearby spacecraft could. Decisions that might take minutes to verify on a mission closer to Earth instead unfold over a rhythm of nearly 2-day cycles, forcing the team to plan multiple steps ahead and build in contingencies for outcomes they won't be able to confirm or deny until the following day at the earliest. When something goes wrong, as it did in 2023 when the spacecraft began transmitting unreadable, garbled data after engineers traced the problem to a corrupted section of memory in its flight data system, troubleshooting an almost 50-year-old spacecraft with extremely limited telemetry, extremely limited remaining memory, and the same brutal 2-day communication delay becomes an exercise in patient, methodical engineering, unlike almost anything else in modern spaceflight. That 2023 memory issue was eventually resolved by carefully relocating the affected code to a different section of the spacecraft's tiny remaining memory, restoring normal, readable data return, a genuinely impressive piece of remote problem solving, achieved without ever being able to physically touch the hardware involved. There's a broader lesson here, too, about just how much of modern deep space exploration actually depends on solving problems in incredibly faint signal detection, well beyond simply keeping Voyager alive. The same fundamental techniques, huge collecting areas, cryogenic cooling, precision signal processing, globally distributed listening stations, also underpin efforts like the search for extraterrestrial intelligence, where researchers specifically design instruments to detect radio signals from potential civilizations that would likely be even fainter and far more distant than anything Voyager 1 has ever transmitted. In that sense, keeping Voyager 1's whisper quiet signal alive isn't just an act of institutional nostalgia for one historic spacecraft. It's part of the same broader engineering effort aimed at eventually detecting far stranger, far more distant signals, whatever those might someday turn out to be. It's also worth noting that Voyager 1 has, in a very real sense, already served as a working proof of concept for exactly that kind of extreme sensitivity search. A 2017 study using the Very Large Array in New Mexico specifically used Voyager 1 as a calibration and demonstration target, confirming that existing radio astronomy instruments were capable of detecting a narrowband signal at a range comparable to roughly 130 astronomical units, well beyond the outer edge of the solar system, using techniques directly relevant to the broader search for potential signals from other civilizations. That a known human-made signal at Voyager 1's distance could be reliably recovered using research-grade radio telescopes gives scientists genuine, tested confidence in the underlying methods used across the wider search for extraterrestrial intelligence, even though no such signal has ever actually been found. So here's where this genuinely stands right now. Voyager 1's transmitter, at just over 22 watts of power, is sending a signal that arrives at Earth measured in mere attawatts, a fraction of a billionth of a watt, roughly 20 billion times weaker than the power needed to run a digital watch. By any conventional standard, a signal this faint should be functionally impossible to recover any usable information from it all. And yet, using a global network of massive cryogenically cooled antennas, precision signal processing, and nearly 5 decades of continuously refined engineering expertise, NASA's Deep Space Network still manages to hear it, track it, and in most cases, still pull genuine data out of it. An achievement so replicable, in fact, that a small team of amateur astronomers using a telescope built in 1956 managed to detect the very same signal on their own. But this isn't a story with an indefinite happy ending. Voyager 1's power source continues weakening every single year, with absolutely no way to reverse or slow that decline. Engineers have already been forced to permanently shut down instrument after instrument simply to keep the spacecraft's transmitter broadcasting at all. And current projections suggest Voyager 1 may run out of usable power entirely sometime in the mid-2030s. When that happens, no amount of antenna size, cryogenic cooling, or clever signal processing will be able to compensate for a transmitter that simply has no electricity left to broadcast with. The faintest signal humanity has ever successfully, routinely decoded will finally, permanently fall silent. The real question isn't whether NASA can keep hearing an impossibly faint signal for now. The last 5 decades have already proven, again and again, that it can. The real question is how many more years of that whisper-quiet conversation remain before Voyager 1's failing power supply finally settles the matter for good, regardless of how sensitive humanity's listening equipment continues to become. If you want to be here for every update on Voyager 1's remaining power and its eventual final transmission, subscribe to the channel and turn on notifications. Because when that day finally comes, we'll cover it here, with the real data, not the invented version. 22 watts? A billionth of a watt. 50 years of listening and counting. Whatever the final year of contact turns out to be, this remains one of the most quietly remarkable ongoing feats of engineering happening anywhere on Earth right now. A global network of giant dishes, cooled to near absolute zero, spending a portion of every single day listening for a whisper, fainter than almost anything humanity has ever successfully decoded, simply because a machine built nearly 50 years ago is still somehow faithfully calling home. Thanks for watching.